Hello class. Okay. Welcome you all of you to in our lecture series of laser. Okay. So previous lecture we have seen three processes: spontaneous emission, absorption, and stimulated emission. In this lecture we are going to understand the condition for the lasing action. Okay. So here is the condition to for the lasing action: stimulated emission required. Yes, we seen in the last lecture. Metastable levels, population inversion, enough number of photons in the system. Okay, so this is SMPE is the condition for to lasing action. Okay, so metastable state is what? Last lecture I gave you the example when electron goes to the excited state. This is your ground state and this is your excited state. It raised up to 10 to the power minus 8 second, which is the ordinary lifetime. But later on, we found some element where this time is 10 to the power minus 3 second. 10 to the power minus 3 second. And this time is really high as compared to the ordinary lifetime. And this 10 to the power minus 3 second state is known as metastable state or metastable level. Okay. So simply in one line we can define metastable level: excited energy level having lifetime 10 to the power minus 3 second, as I told you. Okay, so lifetime of such a state in is 1 lakh times greater than the ordinary excited states. Okay, so the lifetime of such a state is 1 lakh time greater than the ordinary excited state. Okay, so these are the four condition which is required to for the producing to the lasing action. Okay, just understand here one more important process which is really required to producing laser, that is population inversion, which is population inversion. Okay, just see at the normal population or normal state, E1 is your ground state, E2 is your excited state, and number of atoms or number of electrons present at the E1 state is really high as compared to the excited state. But this process is not able to produce the laser, because in order to produce the laser we require high population at our excited state. So this is our excited state and we require very high population in order to produce the lasing action. So therefore we need to some other external energy resource or external energy scheme where we can achieve this population inversion, and this population inversion mandatory to produce the lasing action. Okay, just see here, n1 is the number of atoms in the ground state. N1, suppose n1 is the number of atoms in the ground state, and n2 is the number of atoms at the excited state. Okay, so n2, this is again n2 and this is again n1, so n2 should be greater than n1, and this is the case of population inversion which is required to for the lasing action. Okay, if n2 is less than n1, what will happen? If n2 is less than n1, then stimulated absorption process will dominate over the stimulated emission, and a result light will be attenuated after then getting amplified, or sorry, rather than getting amplified. So therefore we require this population inversion. Okay, so we are cleared about the population inversion, that is E2 is our excited state and number of atoms should be higher at our excited state. Okay, so the according Boltzmann, here is the distribution function is given to us. The number of atoms per unit volume in energy level E is given by this formula: n is equal to n0 e to the power minus e by kt. Okay, where n0 is constant, k is the Boltzmann constant, and t is the temperature. Suppose this is our equation number 1. Okay, meaning of equation is what? At any temperature the number of atoms of higher energy level is lesser than that in the lower energy level. So meaning of this equation is really simple, that number of atoms in higher energy level is lesser than that in the lower energy level. So E1 and E2 is again the two energy levels with the number of atoms in these levels N1 and N2. So if you write the number of atoms for a two state, we will get the equation N1 is equal to N0 e to the power minus E1 upon KT for the E1 state, and N2 is equal to N0 e to the power minus E2 by KT. Okay, if we take the ratio of these two states atom, then N1 upon N2 will equal to the N0 e to the power minus E1 minus into bracket E1 minus E2 bracket complete upon KT. Okay, so at any finite and positive temperature, as E2 is greater than E1, we have N1 is greater than N2. Okay, so this is equilibrium condition. This is equilibrium condition, and stimulated absorption process will dominate here, but we don't require this process. We require the population inversion where n2 should be the larger than n1. Okay, so for stimulated emission to dominate over stimulated absorption, we require n2 should be greater than n1. This is the case of population inversion. Okay, so from the above equation, it is possible only when the temperature is negative. So the state of population inversion is called as the negative temperature coefficient, or sorry, negative temperature state, and the word negative temperature states indicates a non-equilibrium situation. This is non-equilibrium situation. So suppose here is the n1 number of atom is the ground excited state, and here is the n1, that is number of atoms in the ground state, excited state. This is E1, this is E2. Simply this is the scenario of population inversion. Okay, so in order to achieve the population inversion, we require some pumping scheme. So method of producing population inversion. Pumping is what to method of producing population inversion. Okay, suppose we want to lift the water from ground state to the or ground floor to the third floor, we require some other external energy source. Just like we required centrifugal pump to lift the water from ground floor to the third floor. Similarly, if you want to achieve the population inversion, we require some other external pumping scheme where with the help of that pumping scheme we can achieve the population inversion. And yes, there are several types of pumping scheme, just like see here, optical pumping where we are using the powerful light, electrical pumping where we are using the electrical discharge just like which is used in a gas laser. Another is the forwarding biasing which is used in PN junction diode laser, chemical pumping, nuclear pumping, and X-ray pumping. These are the several types of pumping scheme. Okay, another important basic process which is required for lasing action is active system. Active system. Okay, the definition of active system is really simple: an atomic or molecular system with the metastable state and having population inversion. An atomic or molecular system with the metastable state and having population inversion. So active system is characterized by the optical gain amplification, and the active system can be solid, liquid, or gas. Just like take an example of helium neon laser. Okay, so in case of helium neon laser, neon as a active system because it has a metastable level. Okay, and we are getting the lasing light due to the neon atom in case of helium neon laser. Okay, so this is simple active system, atomic or molecular system with the metastable state and having population inversion. Okay, another important mandatory process or important phenomenon is resonant cavity. Here you can see the resonant cavity. Here the resonant cavity always having the length n into lambda by 2, because of if the length is equal to n into lambda by 2, then we will get the constructive interference and we'll get the higher or very high intensity or high intense laser beam as a output. Okay, so for the lasing action, enough number of stimulating photons in the system is required. Suppose this system is here. This can be achieved by the placing the active medium in between 100% reflecting mirror. This mirror is 100% reflective, and another is partially reflecting. Another, this mirror is partially reflecting. Okay, and having the distance is equal to d is equal to n into lambda by 2 uh, as I written here. Okay, so due to such a distance, the laser cavity resonates at y. Resonance is happen here, resonance at lambda, and due to which the laser having wavelength lambda is enhanced, and we are getting here the very high output laser beam. Okay, so this is the role of resonant cavity. Here is the role of resonant cavity also given in detailed way. Enhances the photon in laser having wavelength lambda. Due to distance d is equal to n into lambda by 2, wavelength other than lambda were suppressed due to non-resonance, and thus laser become perfectly monochromatic. Monochromatic means single wavelength, and because of why resonant cavity suppresses other wavelength. Okay, resonant cavity supports positive feedback. First emission is always as a spontaneous emission. Photons produced due to the first few spontaneous emission trigger the stimulated emission of remaining atoms, and the mirrors used across the resonant cavity reflect back the photons, and these photons hits atom present in the laser cavity producing another two photons. And also due to this mirror, photons oscillate in the laser cavity, and when it required to sufficient intensity, it will come out from the semi-transparent mirror. Okay, so positive feedback, it acts as a positive feedback, or it's supposed to the positive feedback. It also provides directionality to the laser. Due to presence of mirror, the photons traveling up axis, the photons which is traveling up axis, okay, suppose this is axis, uh, escape from the cavity, and thus laser along the axis is built up and become more directional. So it is also due to the resonant cavity. Okay, so the cavity oscillation is again here. The oscillation of the photons between mirror, it supports the positive feedback and provides the directional and monochromatic and properties of laser. So this is the role of resonant cavity. Okay, just see here, you are getting one photon produces two photon produces four photon produces eight photon, and photon produces 60 photon. This process goes on and the avalanche effect is created. Okay, so it is the set of processes responsible for to production of laser. There are nine conditions or processes which is required to for the lasing action: pumping, population inversion, first few spontaneous emission, stimulated emission, absorption of the off-axis photons, back and forth oscillation of the photons in the laser cavity, the chain reaction of stimulated emission, avalanche multiplication of the photons, and outermost of the laser through the partially reflecting mirror. These are the nine processes responsible. Okay, so the principle of laser scheme we'll understand in next lecture.